In 2017, a mid-size retail platform ran an internal audit on their order data. They were not looking for a problem. They were preparing for a financial review. What they found was that roughly 4% of their order records had a total field that did not match the sum of their line items. Some discrepancies were a few pennies, some were hundreds of dollars. The records had existed for years. Every one of them had passed every database constraint without complaint. No error had been raised. No alert had fired. The platform had been reporting revenue figures based on those totals. That is not a constraint failure. The database did exactly what it was built to do. It stored the records. It validated the schema. It enforced every rule it had been given. The problem was something the database was never given the tools to catch. Internal consistency is a property of a single record. It is the requirement that the fields within one row, one document, one entity agree with each other, not with other records, not with external systems, with each other. When a record is internally consistent, its fields describe the same reality. When it is not, they contradict each other, and your database returns the record as if nothing is wrong. Think about what that looks like in practice. A customer record where the date of birth is 1990, but the stored age is 67. An invoice where the subtotal plus tax does not equal the total. A user account where the status is active and the deactivated underscore at timestamped is 3 years in the past. A shipment marked as delivered with a delivered underscore at field set to null. None of those records will cause a type error. None will violate a schema constraint. None will be rejected. They will be returned by your query, passed to your application, and treated as truth, because they look like truth from every angle a database is built to inspect. So where does internal inconsistency come from? The most common source is derived fields. A derived field is one whose value can be calculated from other fields in the same record. Order totals are derived from line items. Duration is derived from a start time and an end time. Age can be derived from date of birth. When you calculate a value and then store it alongside its source, you now have two representations of the same fact. If one changes and the other does not, the record contradicts itself. The second source is partial writes. Picture an application running two separate update statements against the same record. One updates the line items, one recalculates the total. The first completes, then something fails before the second runs, a timeout, a crash, a dropped connection. The record is now in a state the application never intended to create. And if neither statement was wrapped in a transaction, the database considers both operations done. One succeeded, one did not. The record reflects the first and ignores the second. The third source is schema evolution. A new field is added to capture something that was previously implied by another field. Someone backfills historical records, but the backfill logic differs slightly from the logic that populates the original field. Both fields now describe the same reality using rules that do not quite agree. They will match in most cases. They will diverge in the edge cases that matter most. None of these causes require an obvious bug. They are structural. They emerge from the gap between what the database enforces and what the data is supposed to mean. There are 3 things you can do about this. The first is to stop persisting values that can be calculated. If a total is derivable from line items, calculate it at read time. Do not store it. A field that does not exist cannot become stale. This is not always an option. Performance sometimes demands denormalization, but when it is an option, it eliminates the inconsistency risk entirely. The second is to push field relationship rules into the database itself. Most relational databases support check constraints that validate relationships between fields within the same row. You can enforce that an end date cannot precede a start date. You can enforce that a status value must be compatible with a timestamped field. These constraints fire regardless of which system writes to the table. That means they protect you even when the application layer does not. The third is to treat consistency as something you measure, not something you assume. Write queries that scan for records where fields disagree. Run them on a schedule. Alert on results. This does not prevent inconsistency from entering your data, but it tells you when it has arrived and how much of it exists. That is a significant difference from discovering it during a financial review. The retail platform from 2017 traced the problem back to 2 update statements that were not wrapped in a transaction. Line items were updating. The total recalculation was not always running when it should. The fix was not complex. Consolidate both operations into a single transaction and run a reconciliation job over the affected records. The records had been wrong for years. The database had returned them without complaint every time. Internal consistency is not about whether your data is valid. It is about whether your data is coherent. A record can satisfy every rule you have written and still describe 2 different realities in the same row. Your database will not tell you when that happens. The constraint system does not see it. The schema does not catch it. That gap between a record that is technically valid and one that is actually correct is yours to manage.